Hello students. In previous session we had talked about Newton's law of cooling and how it is applicable for convective heat transfer case. We talked about convective heat transfer coefficient and the inverse of which is called thermal resistance, and we also talked about the electrical analogy used in heat transfer, where current is equivalent to heat transfer, voltage is equivalent to temperature difference, and resistance is equivalent to thermal resistance. This concept of thermal resistance is quite useful in solving the heat transfer problems, where you can add up various resistances and get the total resistance, and the inverse of the total resistance is nothing but the overall heat transfer coefficient. Let's try and apply it to a real life situation. In this figure you can see a composite wall made up of three different type of materials, say A, B and C, having thermal conductivity equal to Ka, Kb and Kc, and their thicknesses are equal to La, Lb and Lc. Say this is the composite wall of a building, and there is air blowing over the outer surface of the wall, and the temperature of this may be high. Say it's a case of summer, so you have higher temperatures outside, so the hot fluid may be hot air flowing over the surface of this, and you have cold fluid, or inside the room the air is kept cool with the help of, say, an air conditioner. So you have the lowest temperature here and you have the highest temperature here, and as there is a convective heat transfer between air and the solid wall here, while there is conduction through the walls, but the conductivities are different, so the temperature drop slopes may be different, and this is again convective heat transfer resistance in case of the inner or on the inner surface, or that offered by the air layer on the inner surface. So all these temperatures are represented here on the nodes, and you have the inverse of heat transfer, convective heat transfer coefficient multiplied by the area as the resistance for the convective heat transfer, the air layer here, and these are the resistances offered by due to conduction through these walls, and again the resistance offered by the air layer or air boundary layer near the surface of the inner wall surface. So if you add up all these resistances, it will give you the total resistance. So this is the concept of thermal resistance and the total resistance, and the inverse of total resistance is nothing but the overall heat transfer coefficient. So let's take one real life example. You are supposed to solve this example on your own, but enough explanation and hints will be given in this lecture for solving that problem. So application of thermal resistance concept. So here you can see a wall made up of various materials. So this is on the outermost side, it is exposed to atmosphere, so you have outside air film. Then you have the wall made up of brick, face brick, which is 90 mm thick. Then there is an air space in between. Then there is a seating made up of 13 mm fiber board. Then an insulation of 75 mm mineral fiber, again an air space, and then a gypsum board of 13 mm thickness, and finally there is an air film on the inner surface of the wall. So all these components offer different values of thermal resistance to the heat flow. It may be either from the room to the outside or ambient or the other way. Now here it's a heating case, that is the ambient is at a low temperature and the room is kept at a higher temperature, so the heat is trying to leak out from the building through these layers. So let's find out the thermal resistances of various layers. Now in some cases you may have to refer the tables which give you the required values of resistance. So first, if I talk about the face brick, which is 90 mm thick, the inverse of thermal resistance, whose unit is meter Kelvin per watt, would be 0.76. So conductivity is 1 upon 0.76. So this, because this is 90 mm thick, to get the resistance as meter square Kelvin per watt, I will have to multiply it with the thickness in meters. So 0.76 multiplied by 0.090, that gives me the total thermal resistance of 0.068 meter square Kelvin per watt. This much is the resistance offered by the brick wall. Now let's take another component, which is this asbestos sheet, or I think it is this fiber board, which is 13 mm thick. So this fiber board is offering a resistance equal to around 0.23 meter square Kelvin per watt. Now let's take again the next component, which is nothing but the let me check what it is exactly. So it is board and slab glass fiber organic bond. So this is you have this insulation of 75 mm mineral fiber. So if you have a blanket bed mineral fiber 75 to 90 mm thick, it will offer you 1.94 meter square Kelvin per watt of resistance. You can compare the various values of resistance. Higher the value of resistance, better the insulator, and in this case we are interested in better insulation, so that the heat